Elisabeth here again. In this last part on hydraulic systems, we will discuss power efficiency. But first of all, we will look a little bit on the pressure levels, how the variation is if I go through a whole transmission. So here we have pressure and we have length. If I start off from the tank, I have a pressure drop in the first section line. Then I come to the pump. We have a pressure rise. We have a long tube here, and we have a small pressure drop. Then we come to the motor. Here we have the main pressure drop, which the pressure drop that in fact gives something useful out on the shaft from the motor. And then there's always a small pressure drop from this part of the tubes back to tank again. We can also study looking in another system where we have a pump and a cylinder and do the same exercise. First of all, we start from zero. Once again we have pressure and we have length. We start from zero, we have a small drop, we have a pressure increase, a small drop as soon as we have another tube. We have a little drop also over this valve. This can also be dependent on the flow, but in principle we have a small drop there. We have more losses when we go from the valve to the cylinder, and here we have the main drop, which corresponds to if there's an external force on the cylinder. We follow the next tube from the cylinder to the valve. That's this part. We go through the valve once again, and from the valve back to the tank. So this is how the pressure level is, the pressure variation we can see if we go from pump through the whole system and back to the tank again. And the useful pressure drop, that is what we can see here, what corresponds to the pressure difference that is caused from an outer load. The pressure is always a result of an outer load or some restriction. So I can also start from this end and say that, okay, in order to reach the tank, I must push the fluid through this pump. In order to reach this point, I must push it over the valve. I must push it through this pipe. And here we have the pressure difference that corresponds to the outer load. We have to push the fluid through this pump. We need even more pressure to push the fluid over this valve, and this is the point with the highest pressure. This is the level we have to reach in order to have this system going. And if I need to have this pressure from immediately after the pump, I need to have a pressure rise, pressure increase, pressure difference over the pump. So this pressure increase that corresponds to the required torque I need on the shaft to this pump. And there is a little negative pressure that I can have in the very beginning in order to get the fluid from the tank and to the pump. Let's see how we can calculate the losses in hoses and pipes. This is expression that you may be familiar to. You should have met them in the hydrodynamics course earlier. The pressure drop in a tube can be expressed from a friction coefficient, the length, the diameter, the density of the fluid, the mean velocity of the fluid in square, and divided by 2. And the pressure coefficient, the friction coefficient, will find if I have 64 divided by Reynolds number. And Reynolds number I can calculate from the velocity of the flow inside the tube, the density, the diameter divided by the dynamic viscosity. Here to the right you can find a numerical example, and it could be a good idea to stop the video session here and go through this and check that I have calculated it correct. We have earlier met these definitions, some of them. If I have a cylinder that works as an actuator, the power efficiency is the power out divided by power in. This is on the motor side. Out you have a force and a velocity, and in you have a flow on the fluid side. This is on the mechanical side, and this is on the fluid side. You have the flow times the pressure difference over the motor. This actuator. You can divide it into a volumetric efficiency and a mechanical efficiency, and the volumetric is connected to everything that moves, the velocity times the area divided by the flow. The mechanical is related to the forces, the force times the pressure difference and the area. And this is valid if you have approximately the same areas on the low pressure side and the high pressure side of the cylinder. Otherwise you have to make the expression with P1A1 minus POAO. You have to make it clear what's on the high pressure side and what's on the low pressure side. You have to take pressure times the correct area. If you have other components, you can also discuss the efficiency. The power efficiency for a valve, for example, can be described as the flow through the valve times the pressure after the valve on the side that you can call out, divided by flow into the valve times the pressure before the valve. And in the same way you can divide this into a volumetric and a mechanical part. If I then go to the pump and the motor, the rotational machines, the total efficiency for a rotational pump is, out from the pump you have the flow. So you have power out that's related to fluid. That's Q times the pressure difference over the pump divided with what you have on the incoming power that's on the mechanical side of the pump. Torque times rotational speed, rotational velocity. And if you can say that the pressure on the suction side of the pump, on the tank side of the pump, is 0, then you can instead of having the pressure difference here, you can put the pressure after the pump in the equation. You can divide this to a volumetric and a mechanical efficiency, and the volumetric will contain the Q, the flow out, the rotational speed in times the displacement, the size of the pump. And you need that, of course, in order to have a efficiency that is dimensionless. The mechanical corresponding to the mechanical efficiency, that's the pressure difference over the pump, the displacement divided by the torque. Or if you can say that POP on the low pressure side is 0, you only have P at the high pressure side times displacement divided by the torque. For the motor, you have almost the same, but not exactly the same. And it's important that you see the difference between these two, because for a rotational motor, power out is torque times rotational speed. Power in is flow times pressure difference. With the pressure on low pressure side equal to 0, you only have flow times P1, P on the high pressure side. And similar to what we did for the pump, we can do for the motor. We can divide it into a volumetrical efficiency and a mechanical efficiency. The exercise I would like you to do is that check that this expression, volumetric times mechanical efficiency, is equal to the total efficiency, both for the pump and for the motor. I also want you to derive an expression for the total efficiency for the transmission in slide 6, and expressions for volumetric and mechanical efficiency in the same slide. So we can stop there. So let's stop this part with a short review of the system I would like to express the efficiency for. See you in the classroom.